Welcome to today's paper reading. Today's paper is titled, DeepSeek-Prover, Advancing Theorem Proving in LLMs Through Large-Scale Synthetic Data. This paper, authored by Huajian and colleagues from DeepSeek, Sun Yat-sen University, and other institutions, presents an innovative approach to enhance theorem proving in large language models through the use of large-scale synthetic data. The work is currently under review. The abstract highlights how proof assistants like Liang have significantly improved the accuracy and reliability of mathematical proof verification. Despite the promising capabilities of large language models, LLMs, in mathematical reasoning, their progress in formal theorem proving is limited by a lack of training data. To tackle this issue, the authors propose a method to generate extensive Liang 4 proof data from high school and undergraduate-level mathematical competition problems. This involves converting natural language problems into formal statements, filtering out low-quality statements, and generating proofs to create synthetic data. This approach aims to enhance the theorem-proving capabilities of LLMs by providing a rich dataset for training. In modern mathematics, the complexity of proofs has led to significant challenges in peer review. This complexity often results in the acceptance of erroneous proofs, with critical flaws being detected only after considerable time has passed. To address these issues, formal mathematical languages such as Liang, Isabelle, and Coq have been developed. These languages enable the creation of computer-verifiable proofs, but they require significant effort and specialized expertise. Consequently, the importance of automated theorem proving is increasing. Recent advances in large language models have introduced new strategies to guide the search process, but these methods still face challenges due to the vast search spaces required for complex theorems. Automated theorem proving has been a significant area of interest in artificial intelligence research since its inception. Early efforts focused on simpler logical frameworks, leading to the development of efficient first-order theorem provers like and Vampire. However, these tools often struggle with complex theorems found in modern proof assistants such as Liang, Isabelle, and Coq. The integration of deep learning models and model-guided search techniques has revitalized the field, enhancing the capabilities of ADP systems. Neural models have been combined with ADP through various approaches, including tree search algorithms guided by neural models and the use of reinforcement learning to improve accuracy. Another approach involves large language models fine-tuned with open-source proof data, which interact with verifiers to iteratively generate and verify proof steps. Despite high performance, these methods are computationally intensive. Auto-formalization, which converts natural language descriptions into formal statements, has been proposed to address the limited availability of formal corpora. This involves generating synthetic datasets of formal proofs and using large language models to translate natural language problems into formal statements. However, these datasets remain small and limited to specific benchmarks. In this paper, the authors aim to synthesize formal proofs via auto-formalization on a larger scale to improve the performance of a neural prover. The approach consists of 4 key processes. Initially, we auto-formalize informal math problems into formal statements. This involves generating a dataset of 869,659 natural language problems, focusing on algebra and number theory, and fine-tuning the model with the MMA dataset. Next, we filter these auto-formalized statements for quality. We use model scoring criteria and a hypothesis rejection method to curate a refined set of 712,073 high-quality statements. After filtering, we proceed to prove these statements. We employ concurrent proof searches, leveraging the logical symmetry between a statement and its negation to accelerate the proof synthesis process. This dual approach also serves as data augmentation, enriching the dataset with both propositions and their negations. Figure 1 provides an overview of our approach to advancing theorem proving in large language models, LLMs, through large-scale synthetic data. The process begins with the auto-formalization of informal mathematical problems into formal statements. These statements are then subjected to quality filtering and hypothesis rejection to ensure high-quality data. The next step involves proving these statements using a model called DeepSeek-Prover, with correctness verified by Liang 4. To enhance efficiency, We conduct concurrent proof searches for both the original statements and their negations. Validated proofs are used to fine-tune the DeepSeek-Prover, and this iterative process continues until the model's performance improvements become marginal. In this section, we evaluate the performance of DeepSeek-Prover against several baselines. DeepSeek-Prover significantly outperforms GPT-4, achieving 60.2% on the Mini-F2F validation set and 52% on the test set. The Mini-F2F benchmark includes 244 validation and 244 test problems, while the FIMO benchmark consists of 149 formal problems. DeepSeek-Prover successfully proves 4 theorems with 100 attempts per theorem, whereas GPT-4 fails to prove any. Additionally, ablation studies demonstrate the effectiveness of large-scale autoformalization, formal statement scoring, and iterative enhancement in improving the model's theorem-proving capabilities. Table 1 presents a comparison of various state-of-the-art methods on the Mini-F2F dataset. DeepSeek-Prover significantly outperforms other methods, achieving cumulative scores of 60.2% on Mini-F2F valid and 52% on Mini-F2F test, which are notably higher than GPT-4's scores of 25.41% and 22.95%, respectively. The table also highlights DeepSeek-Prover's scalability, showing improved performance with increased computational resources, rising from 30.03% using a greedy approach to 50% at 65,536 generation times. Table 2 highlights the improvement in pass rates for the Mini-F2F dataset at pass at 128 in models trained on formal proofs. The comparison is made between models trained on human-authored theorems from Liang 4's MATLAB and those trained on automatically formalized theorems. The results show a notable increase in pass rates from 25.4% to 48.8% when using autoformalized data, indicating a significant performance boost. Table 3 illustrates the improvement in pass rates for the Mini-F2F benchmark at pass at 128 in models trained on proof data scored differently. The models trained on high-score proof data, classified as excellent, good, and above average, achieved 48.8% on Mini-F2F valid and 42.6% on Mini-F2F test. In contrast, models trained on low-score proof data, classified as fair and poor, achieved 41.4% on Mini-F2F valid and 38.1% on Mini-F2F test. This demonstrates a 4.5% higher pass rate for models trained on high-score proof data, highlighting the effectiveness of the model in filtering out lower-quality statements. Table 4 illustrates the improvement in pass rates for Mini-F2F at pass at 128 across successive training iterations. The data shows a clear trend of enhanced performance in theorem proving facilitated by the incremental integration of synthesized data via autoformalization. This table highlights the effectiveness of iterative enhancement in refining the model's ability to handle complex proofs and increasing the quality and quantity of synthetic data produced. Table 5 illustrates the improvement in pass rates for the Mini-F2F benchmark at pass at 128 in models trained with increasing fractions of synthesized data via autoformalization. The data shows that as the dataset size grows from 1,000 to 8,066,621, the pass rates for both Mini-F2F valid and Mini-F2F test consistently increase. This pattern underscores the importance of large-scale datasets in enhancing model proficiency in autoformalizing natural language questions. Notably, the largest dataset size results in the highest pass rates, indicating a direct correlation between dataset size and model performance. In this section, the authors present 2 case studies demonstrating the application of their methods in autoformalizing theorems. The first case study involves proving the determinant of a specific 3x3 matrix is 0 using the Liang formal language. This example effectively translates the matrix and its determinant into a formal mathematical statement. The second case study addresses an autoformalization with inconsistent hypotheses. The initial formalization incorrectly assumed a universal applicability condition, which was later identified and corrected. The model successfully provided a counterexample to highlight the inconsistency. These examples showcase the model's ability to verify proofs and identify inconsistencies, with further details available in Appendix 8.2. In this paper, the authors presented a method to generate extensive synthetic proof data from high school and undergraduate-level mathematical competition problems. This method led to the creation of 8 million proof data points, significantly improving the performance of the DeepSeek Math 7b model and automated theorem proving (ADP). The model now outperforms GPT-4 and other methods on benchmarks like MiniF2F and FIMO. By open sourcing their dataset and model, the authors aim to advance research in ADP and enhance the capabilities of large language models and formal mathematical reasoning. Currently, the work focuses on algebra and number theory at middle school and undergraduate levels. Future work will aim to expand the diversity of mathematical problems addressed, enhancing the general applicability of their methods in ADP. The broader impact of this research includes advancing automated theorem proving, enhancing the capabilities of large language models and formal theorem proving, and providing valuable educational resources. The authors also emphasize the importance of responsible use of their work, ensuring high standards of data privacy and intellectual property compliance. Thank you for watching.